I'm Georgie from the Barossa Improved Grazing Group, and today we're here at the Flaxman Valley weather station site, which is about a 700mm rainfall across the area. This weather station site is located on Michael Evans's property, and he runs sheep and cattle. This weather station at Michael's place measures wind speed, wind direction, soil moisture, rainfall and temperature. So today at the soil pit we've got Rebecca Tonkin from Adelaide Mount Lofty Ranges Natural Resources Management Board and David Woodard from Rural Solutions. They're going to give you a rundown on the different soils for this area.
Yeah, so this is the Evans property at Flaxman Valley and the soil pit, and you can actually see the parent material down from about 70 centimetres down in that, and this being a sort of meta sandstone type material, and through the profile you can see evidence of some of the other rock types through there, so that there's relic bits of quartzite and some iron rocks as well.
I'm Rebecca Tonkin from the Adelaide Mount Lofty Ranges Natural Resources Management, and we're here today to talk about the soil pit at Michael Evans' place near the weather station. So we've got our topsoil here. This has got the most organic matter in it, and it's quite crumbly, which is good. It means it's got good structure, nice and rounded. The roots can make their way in between, and when it does rain, the water will make its way through all these little cracks to fill the soil. Just underneath it here, we've got a slightly less structured, more compact layer here. Yeah, so this isn't quite as strong, but we've got less roots in it, but those that have made their way through have gone down to this layer here, our third layer. Now this is where most of the rock comes in. It's quite a rocky soil. Some of it's like small gravelly bits like this, mostly quartz. Some of it's quite large chunks. The rocks help with the drainage, but they don't hold any water, they're neutral. So in terms of water holding capacity, these are just taking up space. Now down here a little bit further, we've got quite a lot of roots in the soil. What structure we have is quite good, but we still have gravelly chips and so forth in here. And then we get down to what is basically the bedrock of the soil. This is what the soil is formed on. So there's cracks and splits in it that have become soil, or that soil has washed down through, and the roots are following those, looking for moisture and nutrients. So we do have roots going down quite a long way, all the way down to here, and you can see in here there's different colours, some red streaks, orange, that indicates iron. We've got some yellowish stuff, we've got some little glints of goldy stuff, which I'm afraid is mica, nothing more valuable. And right down the bottom, yeah, we've just got the sort of soft rock that's turning into soil. You can see that there's roots growing along the plains where it's cracked, and these are basically putting out little root acids and plant acids and slowly dissolving into that soil. So we've looked at the horizons and a bit at the structure. The texture of the soil is the makeup of the soil in the sand, the silt and the clay. And the easiest way to do that is in the field is with a hand texture test. So you probably know this test, but I'll just quickly go through it. So you take a handful of the soil that you're from the layer that you're interested in. Oops. Just crush it so that it'll take the water in easily. So we've got our handful of soil here. You just add enough water to it to make it moist. Just give it a little squeeze, add a bit of water if you need to. And pay attention when you're doing this so you can see how easily the water goes into the soil, how well it absorbs it. And this is quite a nice soil and it's picked it up really easily. So work it in your hand, see whether it sticks to your fingers or not. Like, you know, some clays will be really sticky like plasticine. Sands don't stick very much at all. Work it into a ball. Does it hold together in a ball? This one is quite well. Something like a really coarse sand won't hold together at all. You can roll it, see what happens. It starts to crumble in this case. Then you take it and squeeze it out between your fingers, like so. And see how long a ribbon you can get. And in this case, not very much. This is a sandy loam. It holds together in a ball, but it's got quite a short ribbon. And in the feel of it in my hand, I can feel that it's got a bit of organic matter. It's got a little bit of bounce to it. It's not just plain soil. So that's our texture. So we've sort of done the physical stuff of horizons, structure, where the roots are growing. So we looked at where all the roots are, texture. So now we start to do a few sort of basic tests that anybody can do in the paddock. Now, one of those is the water stability test, and over here I've got just an ordinary saucer. It's got some water in it, and I've put a crumb of soil from each of the layers. So this has just got distilled water in it, and that's the top soil, the very top 5 centimetres, 5 to 10, 10 to 20, and below 30. And these are just crumbs of soil sitting in the water to see whether they break up or disperse when they're wet. And as you can see, they are sitting here quite happily. Some of the lower ones have fallen apart a little bit, but they are deep in the soil. And the topsoil's got that good strong structure, which means that when it does rain and it gets wet, it's not going to fall apart and just get washed away. Which means that they're stable in water. If they dissolved or fell apart or the water turned milky, that would show that the soil was less stable and it might be sodic, slumping or slaking. And in a hilly ground especially, having stable soil that when it gets wet it just stays in place and soaks up water like a sponge is a really good thing to have. So that's great for here. I've also, on these samples here, taken soil from each of the layers as we go down. So this is the very top soil. This is just underneath it, so about 5 to 10 centimetres right in that root zone. This is about 10 to 20. Here we've got about 30 and about 50. So this is a home soil pH test kit. They're, you know, pretty accurate for pH water measurements. Just place a drop on each one, or a couple of drops. And I didn't do this in advance because the colour changes over time. And the white powder allows you to see the colour of it quite clearly. So this one, probably about 6.5 in the top 5 centimetres. We're coming back to 5.5 to 6 at 5 to 10 centimetres. Definitely about 5 in the 10 to 20. About 5.5 from 20 to 30. And then around 40 centimetres we're back to a neutral 7. So we'll now go to the soil chemistry. Now about a month ago, when we were deciding which area to dig the pit in, we took samples using a corer down the profile. So we've got the soil chemistry data and test results back from the lab, and so we know what all the nitrogen, phosphorus, potassium, sulphur, the minor and trace elements are for these layers. So I'll just go through sort of the highlights, those things that would be really important when you're making decisions as to what to do with this paddock. And the first thing for this one is the pH. We saw with the pH test kit that we had some acidity in this layer, and the lab data backs that up. So we've got a pH of 4.9 for the paddock generally in the top 10 centimetres, and while the pH is, now when I say 4.9, that's 4.9 in calcium chloride. Now calcium chloride pH measurement is the better measurement to do, but pH water is what that one gives us. pH water is generally about 0.8 of a unit higher, that is more alkaline, than pH calcium chloride. So when we've got a 6 with our pH water, we've probably got about 5.2 in calcium chloride, more or less. When we have a pH of 5.5 in water, then we've got a pH of about 4.7 calcium chloride, and at that level toxic aluminium is starting to affect plant roots. So what we've got in our pH calcium chloride here is 5. We've got 4.6 in this zone, 4.7. So this area here is likely to have aluminium toxicity. And then we go from 4.8 to 5.2, and if we were able to do deeper, it would probably become more neutral. So that's something to look at there. When we did the tests, we also requested aluminium, which is toxic to plant roots, as I said, and the aluminium measures for this show that there is a slightly toxic layer of aluminium in that area. So that is, you know, it's all coming together. The reason why the topsoil is not quite so acidic is because all this organic matter on the surface, manure and so forth, it's basically carbon, and carbon helps to neutralise. But because it's a pasture paddock, it just accumulates in that top zone there, and underneath it stays like what normally happens. When you apply lime, or if lime has been applied in the past, that also makes its way down quite slowly over time, over a few years. So if lime had been applied, it would have affected this area first, and then if there's still lime left, then it hasn't all been used up and neutralised, then it will slowly make its way down. Some other things to note in the chemistry. At the time of sampling, the nitrate was fairly low. Nitrate does go up and down a lot through the season, but you know, it might be that the paddock could do with a little bit of nitrogen to give it a boost just at the start after the first rains have come through. Get it going. The phosphorus levels were quite good for this paddock. We had a Colwell phosphorus of 27, and for this pasture and rainfall and soil type, that would mean that there was enough phosphorus freely available to the pasture, but not excessive. So it's not likely to get leached or washed away. Organic carbon levels, quite reasonable. 3.7 for the paddock in general in the top 0 to 10, which is good. Potassium levels good, boron is fine, sulfur good. In the trace elements though, we found there was a little bit low in copper. So copper might be something to look at supplementing for the health of both the pastures and also for the sheep and cattle that graze on it, because it's an essential element for both plants and animals. Zinc was fine, and iron and manganese were also good. If this area was limed, I would keep a watch on the manganese level, because manganese becomes very available in acid soils but becomes less available in neutral or alkaline soils. So it might go from high to moderate, or from moderate to low. At the moment it's in a good range, and I would expect it to remain adequate. So when we look at the cations, that's calcium, magnesium, potassium and sodium in the soil, we notice that the calcium's a little bit low, and the ratio of calcium to and magnesium to potassium indicates that relatively speaking, the calcium and magnesium together are a little bit low as well. Now, if we have too much potassium related to calcium and magnesium, that increases the risk of grass tetany in stock. So the cattle and sheep have a slightly higher risk of that. Now, if this was limed, which is basically putting on calcium carbonate, the calcium would immediately go up, which would reduce the risk of that grass tetany. And finally, we'll talk about the water holding capacity of this soil. So we've got a nice loamy soil here, going down to a sandy clay loam with the rocks in it. Now, if we add up the water holding capacity of all these layers, which has very kindly been calculated for us, in the root zone, so we've got roots down to about 80 centimetres. If there were no rocks in it, we'd have a total water holding capacity of approximately 71 millimetres of water. So going from completely dry to full of water, we'd be able to get 71 millimetres out of our soil sponge. Or to be precise, the plants would get 71 millimetres out. And if you figure that, you know, leaving aside about 30 mils for, you know, for the soil to have, you've got 41 mils left, and you can calculate approximately how much pasture you can produce out of that. However, we do have these big chunky rocks in it, and those rocks don't hold water. So if we calculate that we've got, you know, maybe 50% rock in this soil, that takes it to approximately 35 mils of water holding capacity here, just depending on how rocky it is in any particular area. Still quite a good amount of water holding capacity though, and a lot of that is due to the organic matter and the loaminess, which means that these soils, when they take in water, they'll take it in very readily and hold it, but they'll also give it up to the pasture quite readily. Clays hold on to water a lot more strongly, and it's harder for plants to get them out. Okay, so another point about the water holding capacity of the soil, from the weather station results, we've seen that this site has the driest soil of all of the 4 stations that are set up, but it also has the highest rainfall. And we think that the most likely reason for this is the perennial pasture, with the deep roots that are growing all the way down deep into this soil here. So basically, whenever the rain falls, there's plenty of roots there, and there's living plants. Even now in March, there are living plants here, phalaris, deep-rooted, some are active, that are taking every drop of moisture and making the most use of it possible.
Thank you very much to the landholders who allow us to use their properties for this project. If you'd like to find out more about this project or the weather station project, please visit our website at www.biggroup.org.au. This project was delivered by Adelaide Mount Lofty Ranges Natural Resources Management Board and funded through the Australian Government through the National Landcare Program.